I want you to imagine, just for a second, that you're standing right in the middle of a massive enterprise data center. The air conditioning is blasting, so it's, freezing cold, and the ambient noise of 1,000 server fans is absolutely screaming in your ear.
Oh yeah, it is not a relaxing environment.
Right. And you're holding a replacement part, and your job today is to perform physical maintenance on a multi-million-dollar PowerStore appliance. Oh, and one more thing. You have to do this without taking down the company's critical data.
No pressure, right?
Exactly. No pressure at all. You have exactly 90 minutes to prove you can pull this off without causing a complete disaster. So that is the reality of the D-PST-MN-A-01 exam. 60 questions stand between you and certification, and you need a 63% to pass.
It's an incredibly high-stakes environment. I mean, in the world of enterprise storage, knowing the underlying architecture is what separates a smooth operation from a catastrophic outage. And just to cover the basics, the exam is delivered in English, and it throws both single and multiple response questions at you to really test if you truly understand that architecture.
Right, which is why today, for this deep dive, we are not just going to read you a list of answers to memorize. We're taking 10 actual practice questions from the source material, and we're going to perform a step-by-step analysis.
Breaking it all down.
Exactly. We will read the full text of every question and completely break down every single option, A, B, C, and D, to really explain the why and the how behind the engineering.
Because in that cold, noisy data center, guessing just isn't an option. You really have to understand the mechanisms of how these machines actually operate.
Absolutely. So let's step right into that physical reality. Before we touch the software or perform any upgrades, we have to safely interact with the physical hardware.
Right. Which
brings us to question 1. Let me just read the full text of the question here. It says, when replacing a component inside the PowerStore base enclosure, what is the mandatory first step regarding static discharge?
A very real scenario.
Yeah. And here are your 4 options. Option A is stand on an anti-static mat without wearing a wristband. Option B is touch the exterior metal chassis briefly before starting. Option C says attach an anti-static wristband and connect it to a known unpainted grounding point. Or option D, ensure the ambient room humidity is below 20%.
So the correct answer here is option C. You absolutely must attach an anti-static wristband and connect it to a known unpainted grounding point.
Okay, let's unpack this because, let's look at the other options. My instinct says option B, touching the metal chassis, or D, keeping the room dry, would make sense.
It's a really common misconception.
Right. I mean, why aren't they enough? It feels a bit like trying to put out a fire with a glass of water versus a fire hose.
That's actually a great way to put it. Let's look at option D first, the humidity. From a physics standpoint, extremely dry air actually increases the risk of electrostatic discharge, or ESD.
Wait, really? Dry air makes it worse.
Yeah, moisture in the air naturally helps dissipate static charges across surfaces. When the air is overly dry, it acts as an insulator. So the static charge on your body has nowhere to go until you touch a highly conductive microchip.
Oh, wow. And then you get a sudden damaging arc of electricity.
Exactly. You become a walking lightning bolt. And for option B, touching the chassis briefly only discharges the static buildup for that exact millisecond.
Ah, I see.
The moment you shuffle your feet, shift your clothing, or, simply move your arm, triboelectric charging occurs. Your body just generates a brand new static charge.
So you're right back where you started.
Right. Option C, the wristband, provides continuous grounding. It's an open channel that drains the charge away the entire time you're working.
Makes sense.
And just to round it out, option A is incorrect because standing on an anti-static mat without a wristband simply isolates you. You're still holding the electrical charge.
Okay, so the wristband keeps us from frying the motherboard. But that protection doesn't really mean anything if we pull the wrong motherboard.
Definitely not.
Which brings up a massive logistical problem the exam covers in question 7. Here's the full text. If a technician needs to physically locate a specific node in a noisy, crowded data center, which feature can be activated from the management interface to assist them?
Another classic scenario.
Right. So the options are option A, the automatic diagnostic data collection tool. Option B, the audible system alarm siren. Option C, the internal cooling fan override speed. And option D, the hardware chassis identify LED.
You're going to want option D here. The hardware chassis identify LED.
Okay.
Activating this turns on a highly visible, blinking light directly on the physical hardware you need to service.
See, I have to ask about option B, the audible siren. Why wouldn't we just trigger an alarm so we can just follow the sound? It seems logical.
Well, it comes down to the physical environment you described earlier. The noise floor in a typical enterprise data center is around 80 to 90 decibels.
Oh, right. It's just a sea of screaming cooling fans.
Exactly.
Yeah.
Trying to hear a small internal speaker on a server chassis in that room is like trying to find a friend at a loud rock concert by having them yell your name.
Yeah, that's not going to work. You'd need them to wave a flashlight or something.
Spot on. You need a visual beacon, which is option D, and that's also why option C, ramping up the cooling fans to maximum speed, fails. You just cannot hear one fast fan in a room of 10,000 fast fans.
That makes total sense. And what about option A, the diagnostic data collection tool?
That is a purely software-based function. It's used for pulling log files. It doesn't trigger any physical, real-world indicator in the room at all.
All right, so we're continuously grounded and we found our flashing LED. We're physically ready to work. But before we pull a part out, how do we prep the system for surgery without crashing the entire company's database? Let's look at question 3.
Let's do it.
The question is, when preparing to replace a faulty node in a PowerStore appliance, what specific operational state must the node be placed into before physical removal?
Okay, the options.
Right, the options are option A, maintenance mode, option B, standby state, option C, service mode, or option D, diagnostic mode.
The exam requires you to select option C here. Service mode.
Service mode. Okay.
Yeah. What's fascinating here is how this operational state is engineered specifically to isolate the node from the storage cluster safely.
Just to be clear for the listener, how does service mode actually create that isolation? Like, what is physically happening inside the machine?
Well, when you trigger service mode, the system actively halts all incoming read and write operations for that specific node.
Oh, okay.
It takes any data currently sitting in its volatile memory, the cache, and flushes it over to its active partner node or down to the permanent drives.
So it's saving everything first.
Exactly. Once that data is safely destaged, as we call it, it logically severs its connection to the storage network. The node is still powered on, but it is completely blind and deaf to the network.
Meaning you can physically remove it without interrupting data flow or, causing corruption.
Right. And that explains why precision in terminology is so critical here. The other options might sound perfectly reasonable.
They really do. I mean, maintenance mode sounds like exactly what we're doing.
They mean different things in PowerStore architecture, though. Maintenance mode, option A, is often used in other IT systems, but here it's not the designated state for physical hardware removal.
Ah, I see.
And standby state, option B, usually implies a lower power state waiting for activation, not a strict I/O isolation.
Gotcha.
And diagnostic mode, option D, is just for running internal software tests. Only service mode guarantees the strict data protection required for hardware extraction.
Precision really matters. Now, let's talk about upgrades. Touching the software can be just as terrifying as touching the hardware if you do it wrong.
Oh, absolutely.
Here is the full text for question 9. Before initiating a non-disruptive upgrade on a PowerStore cluster, what is a mandatory preliminary step to ensure the process will not fail?
Crucial step here.
Right. And the options are option A, migrating all volumes to a secondary cluster. Option B, disabling the storage network switch torts. Option C, formatting the internal system drives. Or option D, running a health check to verify cluster readiness.
The mandatory step is option D, running a health check.
Okay, option D.
Yes, a health check is an automated sweep that verifies everything from drive status to network connectivity. It basically ensures the system can actually survive the upgrade process without dropping service.
See, my instinct says option A is the right answer, migrating all volumes to a secondary cluster.
A lot of people think that.
Yeah. I mean, if we are going to upgrade a system, shouldn't we move all the critical data off it first? Isn't that the safest bet?
Well, while moving data away guarantees the data is safe, it completely defeats the core premise of the question.
How so?
The exam is testing you on a non-disruptive upgrade. In modern enterprise storage, the entire architectural genius is that the system can upgrade its own operating software while the data stays exactly where it is.
Oh, right. It seamlessly serves client requests during the upgrade.
Exactly. Migrating terabytes of data to a whole different cluster is a massive, highly disruptive manual intervention. It takes hours.
Ah, I see. We want the system to handle it internally.
Precisely. And if we look at options B and C, they actively destroy the environment.
Oh, wow. Really?
Yeah. Disabling the storage network, switch ports, option B, instantly severs the connection between your host servers and the storage. That causes an immediate massive outage.
Definitely don't want that.
And option C, formatting the internal system drives, literally erases the operating system and the data. So a health check, option D, is the only non-destructive logical prerequisite.
Do not format the drives right before an upgrade. Good tip.
Very good tip.
Let's move on to question 4, which deals with replacing an internal part, specifically a battery. What must be verified before removing a node that contains a faulty internal battery backup module? Option A, the peer node must be healthy and operating normally to sustain host traffic. Option B, the cluster must have its data encryption disabled temporarily. Option C, the expansion enclosures must be fully disconnected. Or option D, all host servers must be disconnected from the storage network.
The correct answer is option A. You must verify that the peer node is healthy and operating normally to sustain host traffic.
Okay, this feels a lot like a trapeze act.
A trapeze act.
Yeah, like you don't let go of your swing until you are 100% sure the peer node, in this case, is ready and able to hold your weight.
That is a highly accurate analogy. PowerStore appliances operate in active pairs. Both nodes are constantly swinging together, sharing the workload.
Right.
If you physically pull one node out of the chassis to fix its internal battery, the peer node suddenly has to take on 100% of the input and output requests.
So if that peer node is already struggling.
Exactly. If that peer node is degraded or failing, the whole system crashes the moment you remove its partner. You have to verify option A.
And what about the other options?
Well, they're all pretty disastrous actions.
Oh, boy.
Yeah. Option B, disabling data encryption, exposes sensitive data and is just completely irrelevant to hardware replacement.
Makes sense.
Option C, disconnecting expansion enclosures, literally removes the physical hard drives from the system. That obviously breaks access to the data.
Right. Bad idea.
And option D, disconnecting all host servers, deliberately causes the exact downtime you're trying to avoid. You really just rely entirely on the healthy peer node.
So the catcher takes over. But all this redundancy relies on electricity, which leads us directly to our next section, power dynamics.
Very important topic.
Absolutely. Let's look at a planned shutdown with question 2. During a planned maintenance window, you need to completely power down a PowerStore appliance with attached expansion enclosures.
Okay, standard procedure.
Right. After shutting down the nodes gracefully, in what order should the power cables be removed? Option A, disconnect the base enclosure first, then the expansion enclosures. Option B, disconnect the expansion enclosures first, then the base enclosure. Option C, disconnect all even-numbered power supplies first, then the odd-numbered ones. Or option D, the order of disconnecting power cables does not matter after a graceful shutdown.
The required physical order is option A. You disconnect the base enclosure first, then the expansion enclosures.
Okay, I relate this to shutting down a desktop computer. You always shut down the actual computer tower, the brain, before you go yanking the USB cables out of your external hard drives.
Perfect analogy. And the reason that works is because of how the system handles incomplete data. The base enclosure is the compute brain.
Right.
It holds data in its cache that hasn't been written to the permanent drives yet. If you choose option B and disconnect power to the expansion enclosures first, the base enclosure is still running, but suddenly all of its storage disks just vanish.
Oh, that sounds like a panic situation for the system.
It is. The operating system panics because it can no longer write its data. That leads to severe kernel errors and potential data corruption.
So you have to cut power to the brain before the limbs.
Exactly right. Option C, alternating even and odd power supplies, is just a completely fabricated distractor for the exam.
I thought so.
And option D is false because in enterprise hardware, power sequencing always matters to protect data integrity.
So that is a planned shutdown. But, what happens when the power loss isn't planned? Let's check question 5.
Let's hear it.
One of the power supplies in a node has failed. The node continues to run. What system design principle allows this? The options are option A, the power supplies operate in a clustered active-passive mode. Option B, the power supplies provide redundant power to the entire base enclosure. Option C, the failing node borrows power from the expansion enclosures. Or option D, the internal battery backup unit takes over the primary power load.
The design principle at work here is option B. The power supplies provide redundant power to the entire base enclosure.
Okay, redundant power.
Right. If we connect this to the bigger picture, the system is designed so that if one power supply dies, the remaining healthy power supplies instantly carry the entire electrical load with zero interruption.
See, Why wouldn't it be option D? Don't these nodes have internal batteries exactly for this reason? Like a laptop battery kicking in when you unplug it?
It's a critical distinction to make. An internal battery backup in an enterprise node is not designed to run the massive processors and memory of the system indefinitely.
Oh, really?
Yeah. Its sole purpose is to keep the node alive for just a few minutes, just long enough to safely destage volatile cache data down to the permanent NVMe drives during a total catastrophic facility power loss.
Ah, okay. That makes sense. It's a last resort life raft and not a secondary engine.
Precisely. It cannot carry the primary continuous operating load. And option C is incorrect, because nodes and expansion enclosures operate on entirely separate power domains. They can't borrow electricity from each other.
Got it.
And option A is wrong, because the power supplies share the load simultaneously. They don't sit completely passive waiting for a failure. So redundant, active power, option B is the answer.
So redundant power keeps the lights on, but if the appliance can't talk to the host servers over the network, it is just a very expensive, very heavy, humming metal box.
Very true.
Let's talk about keeping the connection alive with question 10. Here's the full text. When cabling a new host to a PowerStore appliance for high availability, how should the connections be distributed?
Okay, network architecture.
Option A, all connections should go to the primary node to minimize latency. Option B, connections must be split evenly between node A and node B. Option C, only the top network mezzanine card should be used for host traffic. Or option D, connections should be routed through a single dedicated storage switch.
To achieve true high availability, you must choose option B. Connections must be split evenly between node A and node B.
Okay, split evenly.
Yeah. Software running on the host, known as multipath I/O, balances the traffic across these split connections. If one path fails, the software automatically reroutes data down the surviving paths.
Here's where it gets really interesting. I have a theory on why people might get this wrong.
Let's hear it.
Instinct tells you that routing everything through a single, incredibly fast, dedicated switch, like option D says, or dumping all the traffic directly onto the primary node. Option A would give you the absolute best speed and lowest latency. Why does an enterprise architecture prioritize that?
That's a great question, because raw speed means absolutely nothing if the system goes offline.
Right.
You're highlighting the concept of a single point of failure. In data center engineering, avoiding a single point of failure is basically the holy grail.
So you want multiple paths.
Exactly.
Yeah.
If you choose option A and put all your cables on the primary node, what happens when you need to reboot that node for a software upgrade? Your entire host connection is severed.
The data stops flowing.
Right. And if you choose option D, routing everything through one single switch, what happens if that switch suffers a hardware failure?
Everything goes down.
Every single server connected to it loses access to its storage simultaneously. Option C arbitrarily limits you to one network card, creating another physical bottleneck.
So spreading it out is key.
Yes. Option B physically eliminates single points of failure by spreading the physical cables across both redundant brains of the appliance.
Split the risk, keep the data flowing. But let's face it, despite redundant power, continuous grounding, health checks, and split cabling, things in the real world still break.
They always do.
When the sirens do sound, how does the system tell us, and how do we gather the evidence to fix it? Let's tackle question 6. Which of the following alert severity levels in the system manager indicates a condition that has already caused a loss of service or data, requiring immediate manual intervention?
Good question.
Option A, critical. Option B, warning. Option C, major. Or option D, informational.
The correct answer here is option A, critical.
Okay.
The definition of a critical alert in this system is that a serious issue has already occurred. Service or data is currently lost, and immediate human intervention is required to restore it.
How does that differ from a major alert in option C? Major sounds pretty severe to me.
It is severe, but the distinction is in the current state of the data flow. A, warning, option B, means you're approaching a threshold.
Yeah.
Maybe storage drive's getting full, but nothing is actually broken yet.
Right.
A major alert, option C, indicates something has physically failed, perhaps a redundant power supply or a single network path. But because of the high availability architecture we just discussed, the system is still fundamentally serving data.
Ah, I see. You've lost redundancy, but not service.
Exactly. The key word in the prompt is already caused a loss of service. When the service actually goes down, that is the definition of a critical alert. And informational, option D, simply logs normal operations.
All right, so we have a critical alert. The system is down. And we need to call technical support. How do we give them the evidence they need to fix it?
The final step.
Right. This brings us to our final question, question 8. A severe performance issue has been reported, and technical support requests diagnostic data. Which feature in the management interface should you use to compile this information? Option A, Performance Analyzer. Option B, Support Assist Telemetry. Option C, System Data Collection. Or Option D, Real-Time Diagnostic Monitor.
To fulfill a request from technical support for deep diagnostic data, you really need to use Option C, System Data Collection.
Do data collection.
Yeah, this specific utility compiles all the historical metric logs, the core dumps, and the deep configuration data into a downloadable bundle that engineers can analyze.
So what does this all mean? To me, this is exactly like taking your car to a mechanic.
Okay, how's that?
If your car is making a terrible noise, you don't just call the mechanic and say, hey, the speedometer says I'm only going 10 miles per hour, which is essentially what Option A, the Performance Analyzer, does.
Right, that's just real-time speed.
It just gives you dashboard numbers. Instead, you need the mechanic to plug their computer into the car and download the entire historical onboard computer log. That is what the System Data Collection does.
Yes, and that distinction between real-time monitoring and historical log bundling is exactly what the exam tests. Option A, Performance Analyzer, and Option D, Real-Time Diagnostic Monitor, are fantastic tools for administrator to look at active, current trends on a screen.
But they don't package up the historical evidence.
Exactly. Option B, Support Assist Telemetry, is a great feature that automatically phones home to the vendor with basic health pings.
Okay.
But when a support engineer is actively working on a severe issue and explicitly asks you to manually compile the deep evidence, you must run a system data collection.
Thank you for joining us as we unpack the physical and digital realities of enterprise storage. Keep studying, keep asking the deeper questions, and we will catch you on the next deep dive.